Hey there, chemists. Welcome to our first lesson in our new unit. This unit is going to be all about reactions and specifically reactions that reach a point called equilibrium. And to kind of jumpstart this unit, we're going to look at rates of reaction and how we can increase the rate of reaction for a chemical reaction. So I wanted to go ahead and start this lesson with one of my favorite videos. So let's go ahead and just take a look. All right, so as you guys can see, a nice quick intro video. Let's go ahead and write down our observations. So again, as I mentioned, we're talking about rates of reaction today. And from that video, what I particularly like about this is I just think it looks so cool. That almost looked fake to me. But in the video, we saw that the rates or the reactions in all four beakers occurred at a different rate. Okay, so they occur at different rates. Okay, and in addition to that, what I also want to point out is not only do they occur at different rates, but something else really important to make note of is that they specifically used two scientists to conduct this experiment because that way they were able to start all the reactions at the same time. So they occurred at different rates, but they were all started at the same time. Okay, all right, so our question really is, why did they occur at different rates? What did those scientists change about each of those reactants that allowed them to occur at a different rate? So before we can get to that, though, I want to take some time to talk a little bit about in order for reactions to occur, there's specific things that need to be true. So taking a look here at our diagram that's provided, what we're looking at is the reaction between carbon monoxide and carbon monoxide and oxygen to create the carbon dioxide molecule and an excess oxygen atom. So taking a look at our first image here, you'll notice that there was no reaction, okay? And from that, right, we note that the two oxygen atoms are colliding, no reaction can occur. However, in our second image, or in the second portion of the image, notice that when the carbon side of that carbon monoxide and the oxygen collide, we are able to produce CO2. So what must be true in order for a reaction to happen? What do we think must be true? Well, it has to do with the way that the molecules are oriented, okay? When they collide again, two oxygens collide, they bounce off one another and no reaction occurs. But when the carbon comes in contact, we are able to produce a reaction. So in order for a reaction to occur, molecules must have or must collide with the correct or what we call proper orientation, or the correct, facing the correct way, essentially. Now, it's not all just about orientation. Orientation is not the only component that has to be true or proper, if you will, in order for a reaction to occur. And so let's go ahead and take a look at our next component. So here we have a potential energy diagram. This potential energy diagram represents the reaction or the synthesis of magnesium and oxygen coming together to form magnesium oxide. And as you can see from our potential energy diagram and our chemical equation, we have an exothermic reaction. Heat is being released. Our delta H is negative. So why does magnesium not spontaneously combust? Well, note that magnesium is one of our reactants, and our reactants start at this point. So why do we not just see a reaction that goes like this? Okay, why do we not just see that? And it has to do with the energy of our substances. Okay, our starting components, our starting reactants do not have enough energy for the reaction, right? If we had enough energy for the reaction, then we would see a spontaneous combustion or a spontaneous reaction right there, but we don't see that. We do have to add energy in, right? We do have to add activation energy. And so in order for molecules, or in order for a reaction to occur, not only do molecules have to have proper orientation, but they also have to have sufficient energy, which is why, again, it's necessary to have activation energy in order to reach that activated complex. So again, reactants must have sufficient energy, okay? And I believe in our video potential energy diagrams, I did kind of label that activated complex as the point at which molecules have proper orientation and sufficient energy to react. So that's our point, but in order for the reaction to occur, we must have these two things. And this is actually labeled under what is called collision theory. So collision theory, which is going to be our basis for all chemical reaction explanation, states that a chemical reaction will occur only if reactants have a collision with sufficient energy and proper orientation. And when we do have these collisions with the proper orientation and sufficient energy, we call these collisions effective collisions. Okay, they were effective in their collision, so they're called effective collisions. And so really everything that we talk about today about increasing rates of reaction is going to be about increasing the number of effective collisions. How can I produce more effective collisions, or collisions with proper orientation and sufficient energy? Okay, so let's take a look at our 5 factors that impact reaction rate. The first factor that's going to impact our reaction rate is the nature of the reactant. Meaning, is our reactant aqueous or solid? Is our reactant an alkali metal or a transition metal? Is it a noble gas or oxygen, right? Just another gas. So let's take a look at these quickly. So, sorry, this should have said ionic and covalent. I'm not sure how that got deleted from there. Okay, but let's start with ionic and covalent. Which is going to react faster? Okay, the one that will react faster is going to be ionic substances. Okay, again, ionic substances can split into their ions. Covalent are bonded together by sharing of electrons. Which will react faster, aqueous solutions or solid substances? Okay, our aqueous solutions will react faster because, again, they are able to split apart and interact with other ions. Alkali metals or transition metals, okay? Alkali metals will react faster. Think about why. alkali metals have only one valence electron. And remember, if you have only one valence electron, then you're going to have lower ionization energy. It's going to be easier to ionize. And lastly, non-noble gas or noble gas, which will react faster, okay? This is going to be the O2, okay? And the reason being is that noble gases already have sufficient 8 electrons on their outside, so they have no need to really react. So the nature of the reactant plays a role. I would say the biggest one that we want to kind of consider here, or the most important one, is probably going to be aqueous versus solid. And I want to be able to explain this in terms of effective collisions. So why do aqueous solutions react faster, okay, in terms of effective collisions? Well, if aqueous solutions dissolve and ionize in solution, allowing the molecules to flow freely, which is going to increase the number of collisions. So maybe not necessarily the effective collisions, but you have to think, if I'm increasing the number of collisions that I have, then I'm also going to be increasing likely the number of effective collisions, okay? So that's the first one, and the nature of reactant is usually asked again in terms of aqueous or solid, and understanding that when the particles can move freely, they can react faster. All right, let's go ahead and take a look at our next reaction. Our next factor that will impact our reaction rate. So the next one we're going to talk about is temperature. So which will react faster, a hot temperature or a cold temperature? Okay. And the winner for which will react faster is going to be the hot temperature. Why do you think that is in terms of effective collisions? Remember, am I changing the orientation or am I changing the energy of my particles? And if I have hotter temperatures, what does that mean about my energy? If I have increased temperature, remember that that means I have increased average kinetic energy. So I'm increasing the amount of energy my particles have. If I have an increased amount of energy, that means that I have an increased number of collisions with sufficient energy to react. Okay, so hot temperatures react faster, faster collisions, more collisions, and key point, more collisions with correct energy or sufficient energy. All right, the next factor impacting rate of reaction is a catalyst. This word sounds familiar to you from your living environment or biology classes, but a catalyst is something that is added that is not part of the reaction, but will help speed the reaction up. So the use of catalyst or no use of catalyst. And the one that is going to impact our rate of reaction is the use of a catalyst. And to kind of explain that why, I want to talk about potential energy diagrams. So catalysts are essentially going to act as matchmakers for your particles. They are going to help bring your particles into proper orientation for a chemical reaction. So how does that impact my actual reaction? What it does is it actually provides an alternate route for your reaction to occur. And it actually decreases the amount of activation energy necessary. It lowers that activation energy. So the use of a catalyst decreases the activation energy, and therefore you have more particles in proper orientation and sufficient energy to react. Okay, so when we have the use of the catalyst, we lower that activation energy. And this is really something that is important. There are lots of questions based on this in our test bank, that how does that use of a catalyst impact the rate of reaction? It lowers the activation energy. All right, we have two more to take a look at quickly. So surface area. So in terms of surface area, which is going to react faster? Okay, is it going to be small surface area or large surface area? So do I want to have more space exposed or less space exposed? And the correct answer is large. We want a larger surface area. That's going to help us increase our rate of reaction. And so what you can think of for this is something, for example, with a small surface area would be like a sugar cube, and something with a larger surface area would be like granulated sugar. Okay, so why does that increase the rate of our reaction? Large surface areas, I'm going to abbreviate, large surface areas mean an increase in the number of exposed particles, therefore increasing the number of collisions, right? So if I have exposed particles in a sugar cube, all of that sugar that's in the center is being surrounded, so the stuff that's in the center can't react until the stuff on the outside reacts. So that's going to slow us down. As opposed to granulated sugar, all of those sugar particles are exposed, so when you throw them in, it's going to react much faster. It increases the number of opportunities to collide. The last one to talk about is concentration. So in terms of concentration, would I want a low concentration or a high concentration? Remember, when we're talking about concentration, we're talking about the number of particles per volume, right? So do I want less particles or more particles? And the correct answer is more particles, right? We want to have more particles as our in our reaction. So if I have increased concentration, okay, that means I have increased number of particles and therefore increased number of collisions, okay? So again, a lot of this can be just thought of as, how can I increase the number of my collisions? How can I make particles collide more often? Really quickly, and then I'm sorry this is long, intro videos usually are, but would pressure have an impact on the rate of my chemical reaction? Okay, and I want you to really think about that, and we're going to actually answer that at the start of class. Do you think pressure would have an impact on the rate of the chemical reaction? Why or why not? All right, everybody, I'm going to attach one of my favorite videos that's kind of silly, but I think it helps remind me of how to increase the rate of chemical reaction as just a fun video. No need to watch it, but if you want to, I think it's cute. Otherwise, I will see you tomorrow. Have a good day, everybody.